this is the first of 5 evenings to go over all of the test questions for the general class license. Those of you who don't know, the general class license gives you many more frequencies, more power, longer distances, a lot more modes of operation. It really opens up a lot of the ham radio hobby for all kinds of things, including emergency services. So it's definitely worth going through this and getting the general class license. Just so you know, this will be 5 evenings, and then we'll have a couple of test sessions scheduled for early November. So they'll come shortly after the review class, and there'll be one on the coast, and there'll be at least one inland. We'll have more information on that later. Just so you know, if you don't have any license at all now, you can still take the technician test and the general test the same day, as long as you pass the technician test first. Now, this is the review class for the general, but there are online resources for reviewing for the technician too. So if you wanted to do technician and general on the same day, you can do that as long as you pass the technician test first. I did that when I tested. So these are all volunteers. We're all members of one or a number of these organizations. These are the local amateur radio organizations: the Mendocino Auxiliary Communication Service, MAX, the Mendocino Amateur Radio Communication Service, McArcs, and the Willits Amateur Radio Society, WARS. The details of this and the links to the recordings will be on the McArcs website. I think it's mcarcs.org. And the good news about this test is they tell you all the questions and all the answers ahead of time. The bad news is it's 420 questions. The test only has 35 questions. You only have to get 26 of them right to pass. But it's a lot of information. And so we've divided it into 5 nights. And tonight is going to be the steepest of the information. We're going to cover 3 sections tonight. The electronic components I'm going to cover. Tim Hanna is going to cover electrical principles. And then I'm going to cover practical circuits. And we're going to try to do all of that in 2 hours. And, the other nights we're going to try to do two sections at a time. They're more complicated. These are fairly straightforward. Just so you know, all of the information is in the ARRL review class, a review license manual, which there's a picture of on the screen now. If you get this book, make sure you get the latest edition, the 10th edition, because all of the test questions changed this year. So you have to get the 10th edition. You can get a really good deal on the 9th or earlier editions, but that won't help you very much. So, you need the latest version of this for the general questions. And everything that we're going to cover tonight is, the questions, the answers, and the explanations are all covered in very detail in this review manual. You can get this from ARRL. I've also seen it on Amazon. I like to buy it from ARRL just because I like to support the organization. I also really like various online test question review courses. My favorite one is at hamstudy.org. If you use it on your computer, it's free. If you get it on your phone or your iPad, it's $4. It's still cheap. It has the advantage that it gives you a sample test, and then it grades you and tells you which ones you got wrong, and keeps track of that. And you can link to the explanation, and it also keeps track of which ones you need to keep paying attention to. So it's a really good way to practice and get up to speed so that you really feel confident when you go to take the test. So there are other ones out there too. I just happen to like the hamstudy.org. Also, the ARRL website has all of the questions and all of the answers. It's the same stuff that's in the back of the review manual, but they're all online. And I found that Wikipedia, if you want to really get into how software-defined radio works, or what a Colpitts oscillator is, or any of the details about radio or electronics, Wikipedia has spectacular, I was really surprised, has actually spectacular information. So if you have questions that the manual doesn't answer, or that one of us doesn't answer, and by the way, we're all available for questions, check out Wikipedia, because it's really great. Okay, so let's get into the test. We're going to do, like I said, I'm going to spend some time on components, and then Tim is going to talk about electronic principles, and then I'm going to talk about circuits. My section should take about a half an hour. We'll take a short break, and then Tim take over after that. So here we go. Let's see here. Okay, circuit components. What's the, oh, and by the way, the answer, this is all multiple choice, and the answer in this case will be C. We'll get to that. But you could be sitting next to somebody that has exactly the same test, but the letters will be different. So you can't copy somebody else's test. It's all, you need to pay attention to the answer, not the letter of the answer. So I hope everybody understands that. So what's the maximum allowable discharge voltage for a 12-volt lead-acid battery? The answer is 10.5 volts. Now, I'll give you a little trick about taking this test, is that it's often the case, not always, but often the case, that two of the answers are ridiculous. And so you've got a 50-50 chance of getting it, even if you don't know the answer. Now, hopefully you'll know the answer, but in this case, a 12-volt battery, the minimum discharge voltage is not 12 volts, and it's not going to be 6 volts. So it's either got to be 8.5 or 10.5. It's actually 10.5. And in fact, if you're using a lead acid battery and it discharges below 10.5, you may have just ruined the battery. So the newer technology, the lithium iron phosphate batteries, are better than that. But if you're using a lead acid battery like in your car, this is what you need to know. Okay, what's the average batteries? What is the advantage of a batteries with low internal resistance? Okay. Long life, high discharge current, high voltage, or rapid recharge. The way to think about a battery isn't just a battery, it's a battery and a resistor. And the older the battery gets, the bigger that resistor gets. But if you think about a battery this way, then you'll see that the more current you draw, the more voltage drop there is across the resistor, and therefore the lower the output of the battery, and the more limited the current is. So the answer to this question is B, high discharge current. What is the approximate forward threshold voltage of a germanium diode? This is also true of a germanium transistor. And the answer here, you just got to memorize this. It's 0.3 volts. If you're in electronics at all, you'll know this, but just remember, germanium is 0.3 volts for the diodes or the transistors. What are the characteristics of an electrolytic capacitor? When you look inside a radio or a TV or anything, and you see these big cans, they're usually the largest components on a circuit board. Those are electrolytic capacitors, and that's what it's talking about. These are all examples of electrolytic capacitors. There are many that are bigger and some that are smaller. But so the choices are tight tolerance, much less leakage, high capacitance for a given volume, or inexpensive. The answer is high capacitance for a given volume. These are not tight tolerances. They do have leakage. And in fact, if something's wrong with your radio or any electronics, and the electrolytic capacitors are old, sometimes you can fix it just by replacing the electrolytic capacitors. They just fail after a time. Another thing about electrolytic capacitors is they are all polarized. So if you replace them, or if you're building a circuit yourself, you need to pay attention to the plus and minus, because if you reverse the voltage, they will explode. Had that happen. So electrolytic capacitors, high capacitance for a given volume. Okay, what is the approximate forward threshold voltage for a silicon junction diode? And again, this is also true for a silicon junction transistor, and it's 0.7 volts. In other words, you have to bias it over 0.7 volts to get the current to flow in the forward direction. And again, you'll just have to memorize this if you don't already know it. Why should wire wound resistors not be used in RF circuits? Well, the key is right there in the question, wire wound. A lot of times, very high resistance or very high power resistors are just a resistive wire wound around a form. There are a couple of pictures here of those. The choices are the tolerance value would not be adequate, the inductance could make the circuit performance unpredictable, the resistor could overheat, and the resistor's internal capacitance would detune the circuit. The answer is inductance, and the answer is kind of obvious if you look at the picture, because wire wound resistors are just coils. They're just coils of nichrome wire. So so at DC, they're just resistors. But above DC, for higher frequencies, they turn into resistors and resistors and inductors. So the inductance of a wire wound resistor makes it inappropriate for anything above DC. What are the operating points for a bipolar transistor used as a switch? Bipolar transistor is the most common type of transistor. They're used for either amplifiers or switches. And here it's talking about using it as a switch. And the choices are saturation and cutoff, the active region between saturation and cutoff, the peak and valley current points, and the enhancement and depletion mode. Well, we're not talking about enhancement or depletion mode. We haven't talked about peak or valley current points. So it's either saturation and cutoff or the active region. Well, if you're using it as a switch, you're not using the active region, you're using the saturation and cutoff. So the answer is A, saturation and cutoff. Another type of capacitor, what is the following characteristic of a low voltage ceramic capacitor? The picture here is a ceramic capacitor, and you'll see a lot of these on circuit boards too. They tend to be smaller. They tend to be discs. Sometimes they're surface mount devices, but the choices are a tight tolerance, high stability, high capacitance for a given volume, or comparatively low cost. Well, these are not high capacitance devices. They don't necessarily have tight tolerance, but they are comparatively low cost. So the answer is D. Which of the following describes a MOSFET construction? Everybody know what a MOSFET is? MOSFET stands for metal oxide substrate field effect transistor. A field effects transistor is different than a junction transistor in that it uses a field to control the circuit instead of a forward biased or reverse biased junction, as in a bias junction transistor. So the answer to the question is actually in the name. So the gate is what controls the current. So if gate is formed by a back bias junction, well, it's not a junction transistor. Gate is separated from the channel by a thin insulating layer. Well, that's the answer, because you don't have a connection. You have a field effect. The source separated from the drain with a thin insulating layer is not right, and the source formed by depositing metal on silicon is not right. So the answer is B, and the answer is actually right in the name of the device. So, and if you look at the symbol for an FET, whether it's a MOSFET or just a regular FET, the gate has an insulation between on its surface, and that's what controls the current from the source to the drain. So, and that's the thin insulating layer. And by the way, we'll talk about this later, but it's probably worth studying in the review manual the specific schematic symbols, because you're going to be seeing them all the time. What element of a vacuum tube regulates the flow of electrons between the cathode and the plate? Well, first you might say, why are we worrying about vacuum tubes? Well, vacuum tubes are actually still used in some linear amplifiers, and especially if you're using some older ham radio equipment, there will be definitely vacuum tubes. So vacuum tubes are definitely something you need to understand. So the choices are the control grid, the suppressor grid, the screen grid, or the trigger electrode, whatever that is. This is the schematic for a tetrode, and it's the control grid. The answer is the control grid. The control grid, if you have just a triode, you'd have a plate, the control grid, and the cathode, and that's all you need. The control grid would control the flow of electrons. What happens when an inductor is operated above its self-resonant frequency? What happens is it becomes capacitive. So if you have a resonant circuit, the lower the frequency below resonance, the more the inductor looks like a wire. The higher above the resonant frequency, the more it looks like a capacitor. So the answer here is a capacitor. What is the primary purpose of the screen grid in a vacuum tube? This again is the tetrode. Reduce the grid to plate capacitance, increase efficiency, increase the control grid resistance. I don't know why you'd want to do that, or decrease the plate resistance. I don't know how that would work. It's actually to reduce the grid to plate capacitance by adding the screen grid. What determines the performance of a ferrite core at different frequencies? Its conductivity, its thickness, its composition or mix of materials used, or the ratio of the diameter to the inner diameter. It's going to be the composition of the materials. ferrite cores don't really have conductivity. They definitely have thickness, but it's the materials that make the difference in the performance of a ferrite core. What is meant by the term MMIC? This is another one you have to memorize. You'll see this more and more, and this may not have even been on earlier tests. MMIC stands for monolithic microwave integrated circuit. The second M means microwave. So it's not multi-mode, and it's not metal multi-layer, and it's not mode modulated integrated circuit. I don't know what any of those are, but it's a monolithic microwave integrated circuit. The MMICs actually revolutionized high frequency electronics, because before MMICs, everything was done with big vacuum tubes and waveguides. And so MMICs made a giant difference. So the answer is monolithic microwave integrated circuit. Which of the following is an advantage of CMOS integrated circuits compared to TTL? Low power consumption, high power handling capability, better suited for RF, or better suited for power supply regulation? Well, they're typically not used in RF and power supply regulation. The answer is and they're not for high power. Their answer is low power consumption. There's also a noise advantage too to CMOS over TTL. By the way, CMOS is complementary metal oxide substrate, and TTL is transistor logic. TTL was the first integrated circuits, and then CMOS came along later with lower power and some other advantages, different voltages. What is the typical low SWR operation for a 50 ohm BNC connector? Everybody know what a BNC connector is? This is a BNC connector. It's a bayonet type connector. You see them a lot on high frequency electronics, and the answer is 4 gigahertz. What's the advantage of a ferrite core toroidal inductor? Large values of inductance. Magnetic properties of the core can be optimized for specific frequencies. Most of the magnetic fields are contained in the core, or all of these are correct. Well, they're all right. Everything here is right. So all of these are correct. Every one of those is a reason to use a ferrite core. What type of device is an integrated circuit operational amplifier? Well, operational amplifier is an analog device. It's all of the transistors and resistors and everything you need for an amplifier in one integrated circuit. And so it's not digital, it's not microwave, it's not programmable logic, it's analog. Okay, so the answer is D, analog. Which of the following describes a type N connector? It's a moisture-resistant FM connector used to 10 gigahertz. A small bayonet connector for data circuits. A low-noise figure VHF connector, or a nickel-plated PL259 connector. Well, it's not a PL259, and it's not a bayonet. That's a BNC. The answer is A. And this is a type N connector. They tend to be for very high frequencies, and they tend to be more weatherproof. Actually, this one is type N on one side and BNC on the other side. But how is an LED biased when emitting light? In the tunnel effect region, at the Zener voltage, reverse biased or forward biased? Well, it's not a Zener diode and it's not a tunnel diode, so neither of those make any sense. Could either be reversed or forward biased. The answer is forward biased. How does a ferrite bead or core reduce the common mode RF current on the shield of a coaxial cable? By creating impedance in the current's path, by converting common mode to differential mode current, by creating out of phase current to cancel the common mode current, or ferrites expel magnetic fields. Well, the answer is to create impedance by creating impedance in the current's path. And this is to reduce common mode RF current. This is something you will do sometimes if you need to reduce the noise in a cable. What is an SMA connector? SMA connectors, if you have a small handheld 2-meter HT, it'll probably have an SMA connector. So the choices are S to type M adapter, a threaded connector suitable for signals up to several gigahertz, a connector designed for several multiple access signals, or a type of push-on connector intended for high voltage. Well, it's not high voltage, and it's not an adapter. So it's either one of these two. It has to be B, the small threaded connector. And there are male and female versions of that. Make sure you get the right one for your HT. But if you're going to replace the antenna, for example, on your handheld radio, it's likely to be one of these types of connectors, SMA. Okay. Which of these connectors is typically used for low frequency or DC? PL259, BNC, RCA, or Type N? Well, we've already talked about BNC and Type N are for gigahertz, and so is PL259. So it's got to be the RCA phono, and that's just the audio jack. It works for DC, it works for audio, but nothing above that. And you'll see that a lot. You'll see them a lot.
So what are some of the topics in the G5? Well, the electrical principles include reactance, inductance, capacitance, impedance transformation, and resonance. The other concepts are the decibel, current and voltage dividers, electrical power calculations, sine wave root mean squared values, and PEP calculations. We'll tell you what PEP's all about in a little bit. And the third section is resistors, capacitors, inductors when they're connected in series and parallel, as well as information about transformers. If you want more information on these topics, you can look on pages 4-1 through 4-8 of the ARRL 10th edition of the General Class License Manual. You'll find additional information on pages 4-14 through 4-25. So you can get in a lot more and a lot deeper than I'm going to attempt to here. Of those three subcategories, you'll find one question from each on the exam. So there's a lot of things you have to be prepared for, because there's wide-ranging topics within each one of those sub-elements. So I'm going to start off with basically a review of the electrical principles from the technician exam, because you need to know these in order to successfully pass the general class exam. It's not learn it and forget it and never use it again. If you're going to go for the general, you'll need to be familiar with these. So we're going to start off with the very basics. Electrons can be made to flow through an electrically conductive material, that's a conductor, by applying an electromotive force, or EMF. That EMF is the push that makes electrons move along. The basic unit of EMF is the volt, and it's abbreviated as, it's also known as electrical potential. You'll see it in equations with the capital letter E. That resulting flow of electrons that the push from the EMF has made is called electrical current. Current is that flow. The electrical current is measured in amperes, most often referred to as amps. And in the equations, you'll see current abbreviated with capital letter I. So there's a property of conductive materials that opposes the flow of electrons, and that's known as electrical resistance. And electrical resistance, the basic unit is the ohm, and you'll see it abbreviated as R in the equations. So let's talk about DC, which most of the tech stuff kind of focused on, and then also alternating current, or AC. Direct current DC, it just flows in one direction, kind of boring. Alternating current, AC, now that voltage actually alternates between positive and negative. It'll start at 0, it'll rise to a peak, it'll start to fall back, it'll go back past 0, go down to a negative peak, and back up to 0. That's a full cycle. And that the frequency is the number of times per second that full cycle, going from 0 to maximum, back to 0 to minimum, and back to 0. The frequency is the number of times per second. We measure it in hertz. The opposition to AC flow, similar to resistance, is impedance. Okay, impedance, opposition to AC alternating current flow. And just like resistance, the basic unit of impedance is the ohm. And we're going to be getting much deeper into all of these in just a little bit. So another really basic concept that was in the tech test was Ohm's law. And what does Ohm's law does is it defines the relationship between current, voltage, and resistance. And if you think about it, it does make sense. If you have a fixed resistance, the current will increase, the flow will increase if the voltage or the push increases. So if you increase the pressure, and don't make your pipe any bigger, you're going to get more flow through it. So with fixed resistance, current increases as voltage increases. If you have a fixed voltage, the pressure's the same all the time, and you increase that resistance, that's going to decrease the flow. So the current decreases as resistance increases. So there's several ways to write Ohm's law as an equation. I'll show you all of them here. The first one I learned is the E, the voltage, equals the current multiplied by the resistance. Yes, that is correct. Another way to write it is the current equals the voltage divided by the resistance. I equals U over R. And another way to rearrange that equation is the resistance equals the voltage divided by the current. This is it may have been a while for some of you folks, but this is pretty simple algebra in how you rearrange these equations. So I'm not going to get into it because we got a lot more of them coming up. So we've talked about voltage, current, resistance, frequency, AC versus DC. Let's talk about power. Power is the rate at which electrical energy is used. That's the definition. And the basic unit of electrical power is the watt, and you'll see the abbreviation when you're doing calculations. Power. I like this formula, and you will too. Power in watts equals the current multiplied by the voltage. So I like this because it spells pi, and who doesn't like PIE, pi? But that's an easy way to remember it. Power is current times voltage. Again, you can rearrange this. The voltage is equal to the power divided by the current, or the current is equal to the power divided by the voltage. Again, it's a little bit of simple algebra just to rearrange those equations. Okay, so power. As you change power, changes in power level are expressed in decibels, or dB. And really, there's only two questions on the exam that relate to it. And the first one concerns the concept of a 3 dB change. A 3 dB change is a factor of 2 change. So if you have a plus 3 dB change, you're doubling the power. So if you had a radio that was putting out 5 watts and you ran it through an amplifier that put 10 watts out, that's a plus 3 dB gain. So it's a twofold change in power. In this case, it's a doubling. It's a plus 3. If you cut the power in half, that's a minus 3 dB change. And the only other question in the pool regarding dB is this one. What does a minus 1 dB or 1 dB loss equate to as far as the percentage of power? A 1 dB loss is actually a 20.6% loss of power. 1 dB doesn't sound like much, but that's nearly a fifth of your power. There's a whole lot more to dB, to decibels, and how to use them. There's different reference points, whether it's milliwatts or what, and all kinds of abbreviations. The calculations that you would use involve logarithms. So if you want to learn more, and I would encourage you to do so, look at pages 4-2 through 4-5 in the ARRL study guide, and you'll probably walk away confused. But what you need to know for the test are two things. A plus or minus 3 dB is a twofold change, and a minus 1 dB is a 20.6% loss in power. Okay, so now we're going to look at DC power calculations. That's the pi that we just talked about. Power equals current times voltage. There's only 3 questions in the pool. However, two of them, you're going to need to be able to actually apply Ohm's law if you're going to calculate the answer. You can always memorize the answer too. But let's start with the first one that's easy. If you have a 12 volts and there's a zero point 0.2 amp current flowing through that device, what power is it consuming? How many watts? Piece of cake, or pi in this case. You have everything you need to know. Power equals current times voltage, P times equals I times E, 12 times 0.2. Answer is 2.4 watts. That comes from right from one of the questions, one of the three questions. Next one is a little bit trickier because you're given the voltage and the resistance, but you need to calculate the watts. Well, how do you do this? Well, since we don't have I, current, you want to take Ohm's law and figure out what the current will be given the voltage and the resistance. And here I show I equals E divided by R, right here. So we're going to plug that in where the E would go in the up, or where the I would go here. So we have power equals E divided by R times E. Well, that's the same as E squared divided by R. Let's plug the numbers in. 400 squared divided by 800. Answer 200 watts. Again, they want you to not just know Ohm's law, but be able to apply it. Third one, a little simpler. You do have to know a little bit here, though. We have a current of 7 milliamps, 1250 ohms. What's the power? Well, we don't have the voltage. We need to calculate that. So we use E is equal to I times R. So we have to multiply the current and the voltage and the resistance to come up with what that voltage should be. You drop that in substitution, and you come up with power equals the current squared divided by the resistance. Okay, that's fine. Notice that the current is given in milliamps, not amps. So you have to convert milliamps to amps. Well, what's a milliamp? It's a thousandth of an amp. So we have 7 thousandths of an amp, 0.007 amps squared, and then divided by 250. That gives you an answer, 61 milliwatts. There's three questions. There's three correct answers. You can memorize the correct answer that goes with each one pretty easily, or you can test your knowledge and your skill, learn how to apply Ohm's law in solving these equations. Okay, that's DC power consumption. That's easy enough. What do you do with AC power calculation? How do you calculate the power when you've got a voltage that's constantly changing, going up or down? How do you do it? Well, there's a couple of ways. One is to reference the peak voltage. What's the peak voltage? That's the maximum that the voltage goes in one direction or the other. It's not, so if you start at zero and you go up to the highest voltage, and then it starts to drop down, you're at the peak. If you are at zero and you go down to a negative voltage, you hit the lowest voltage and then start heading back up, that's the peak. So the difference between the zero line and the maximum voltage is the peak voltage. Another way is to reference the peak to peak voltage. So that's from the highest positive to the lowest negative. And if you follow the description that I just gave, that makes sense. The peak to peak voltage is going to be 2 times the peak voltage. All right, that's one way to handle it. But I mean, how about these calculations where we just want to know an average voltage? Well, if you're dealing with a sine wave, and all of the assumptions in this section are, for a sine wave, you calculate the root mean squared or the RMS value. So in order to calculate AC power, you may have to plug in the RMS voltage to get your answer. So let's look at some of these. And I'm sorry, I'm going to throw a bunch of equations up here, and you may have to reference the book to follow them. Most of these I pulled directly from question pool questions. So if you're asked to calculate the RMS voltage given the peak voltage, you take the peak voltage and you multiply it by 0.707. So if you have a question where it says if you have a 17 volt peak, what's the RMS? 17 volts times 0.707. The answer is 12 volts RMS. 17 volt peak yields 12 volts RMS. Okay, another way to write the same equation is since the peak, and you'll notice I'm using subscripts here. PK is peak, P dash P is peak to peak, RMS. So in this case, if you want to calculate the RMS and you have the peak to peak voltage, you have to first convert that to the peak. It's 2 times the peak, so you take peak to peak, divide by 2, multiply by 0.707. Oh boy, this one looks like a long one here. What if you are given an RMS voltage and you're asked to calculate the peak to peak? Well, again, you can flip these things around, but the equation that's given in the book, and it's given right here, to calculate the peak to peak from the RMS voltage, you take 2 times 1.414 times the RMS voltage. So here's from the question pool. If you have 120 volt RMS, what's the peak to peak? 2 times 1.414 times 120, 339.4 volts peak to peak. Peak to peak is always going to be higher than the RMS. Okay, and just another definition in here, just to kind of hopefully cement the concept in your head. The power dissipated by a resistor at the RMS voltage is equal to the power dissipated at an equal DC voltage. In other words, the power that is available at the RMS is essentially equal to the power with that's produced from an equal DC voltage. All right, here's some more calculations. Hold on to your hat. How do you calculate peak envelope power? That's what PEP is, by the way. Well, first of all, let's define what it is. Peak envelope power is the average power of one full RF cycle at the envelope peak. I believe that's in one of the questions. So the peak envelope power in watts, it's the RMS voltage squared divided by the impedance in ohms. All right. How do we make sense of that? Well, we'll look at that in a little bit. One thing to keep in mind, there's a couple questions that revolve around this. The peak envelope power is equal to the average power in the absence of amplitude modulation. If you're in an unmodulated signal, unmodulated AM signal, the peak envelope power is equal to the average power. They're equal. Same thing with an FM signal or a CW signal. As long as you're not modulating the amplitude of that signal, PEP equals average. And that means that the ratio between the two is 1.0. Again, one of the questions is ask you that. The ratio is 1.0. So, how do you calculate PEP? If you're given the peak to peak, well, first step is to convert the peak to peak to RMS. And this is from question 14, G5B 14. The RMS, so we need to start with the RMS voltage. Well, in this question, you're told that it's 500 volts peak to peak. So let's convert that to an RMS voltage. So we take the peak to peak, we divide it by 2, we multiply by 0.707, and we come up with a value of 170.675. I'm sorry, again, 176.75 volts RMS. Now we have to plug that in the formula above. So you take, because the question was at 50 ohms. So you take the 176.75 and you square it, and then you divide it by the resistance, which was stated in this question, is 50 ohms. Answer, 675 watts PEP. So 500 volts Peak to peak in a 50 ohm load is going to equate to 675 watts PEP. Another question in this series, you're given an RMS peak to peak voltage of 200 volts. So again, you do the same thing. You convert the 200 peak to peak to RMS, which is equal to 70. Remember, the peak to peak is always going to be higher than the RMS. Plug that RMS into an equation using a 50 ohm load, which was specified. 70.7 squared divided by 50 equals 100 watts PEP. You can also calculate the RMS voltage if you're given the peak envelope power and the impedance by using this formula. And this is actually a square root. It didn't carry over here, but so the RMS voltage is equal to the square root of the peak envelope power in watts times the resistance. And here's an example of that from question 12. Given 1200 watts PEP and a 50 ohm load, what's going to be the RMS voltage? Well, you do the math, answer's 245 volts. Now, I know this is going kind of fast, folks, but we got a lot to cover here. And I'm hoping you kind of see how you have to integrate more than one formula sometimes to derive the answer. All right, let's go through a couple questions here. We already went through the math on this, but how many watts of electrical power are consumed if 400 volts DC is applied to an 800 ohm load? Got to use Ohm's law to figure out what the current is associated with that. If you do the math right, you'll come up with an answer of 200 watts. Okay, what dB change represents a factor of 2 increase or decrease in power? Well, that's our friend, number 3. 3 dB is either plus 3 is a doubling, minus 3 is a halving of power. What's the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? Well, you have to work backwards on that one, but again, if you follow the formulas we just reviewed and do the math right, you're going to come up with an answer of 339 volts. And again, it's the RMS, the peak-to-peak is going to be higher than the RMS, always. So what's the average ratio of the PEP to, what's the ratio of PEP to the average power for an unmodulated character? That's the condition we talked about. Well, when it's not modulated, the PEP and the average power are equal. So the ratio, as they stated here, would be 1. All right, on to some more concepts here. Impedance and reactance. So we talked about impedance earlier in the quick review. It's the opposition to AC current flow in a circuit. It's known as impedance. It's defined, in this case, this is in one of the questions, it's defined as the ratio of voltage to current, and it's measured in ohms. And actually, if you look at Ohm's law, that's the same ratio is voltage to current. So impedance in an AC circuit is the opposition to flow, is defined by the ratio of voltage to current. We measure it in ohms. I don't know why they throw this one in there, but it's one of the questions. What's the inverse of impedance? 1 over the impedance. The term is admittance. So inverse of impedance is admittance. Okay, now things get really interesting. Let's talk about reactance. Got resistance, impedance, now we've got reactance. What the heck is that? Well, as Mike kind of touched on, inductors and capacitors, some of the components he talked about, they actually respond differently to AC versus DC. Inductors let DC pass, but they'll block AC. Capacitors will block DC, but allow AC to pass. But the whole game changes when you're looking at specifically AC. Both of them will actually oppose the flow of AC. So that property is known as reactance. The fact that an inductor or capacitor will oppose the flow of AC, it's showing its reactance. Again, it's measured in ohms. We'll see it written as X in formulas. This is an important thing to know. Here, the inductive reactance, X sub L, increases as the frequency increases. So the reactance of an inductor goes up as you increase in frequency, and capacitors are just the reverse. The capacitive reactance decreases as frequency increases, and that leads to some magic. You can add an inductor and a capacitor in what's known as an LC circuit. L for inductor, C for capacitors. They can be combined in an LC circuit, and you can do it either in parallel with the components side by side or in series end to end. And their behavior is different. The magic occurs at resonance. This is a term you need to know. That's the frequency where the capacitive reactance and the inductive reactance cancel each other out. They're equal. And so resonance occurs where the capacitive and inductive reactance cancel, and that's a magic frequency. If you happen to put an inductor and a capacitor in series, forming a series LC circuit, when you reach that resonance point, the impedance drops dramatically. So it might be a way to filter out a signal. If you have a signal at a certain frequency that you don't want getting through, you make a series LC circuit that's resonant at that frequency. The impedance will be very, very low, and the current will flow, and your signal will be dissipated. What are transformers? Well, basically, they're two inductors that have overlapping magnetic fields, and that's known as mutual inductance. There's quite a few ways to make them. Mike talked about ferrite cores, toroidal cores. Those are transformer cores, but typically what the transformer is going to be two sets of windings, wire windings, on a common core. That common core allows them to share their magnetic fields, that mutual inductance. So what do you use transformers for? Well, they can be used to transform AC voltage or impedance. You can shift them up or down. So you can use, that's why they're transformers. They can transform the voltage or impedance up or down. And one of the most important things you need to know is that the change in voltage or impedance from one side of a transformer, from one set of windings on the transformer to the other set of windings, that is proportional to the ratio of the primary and secondary windings. So you have one set of windings, wire windings, known as the primary, and the other set is the secondary. And let's talk about that. Because in a transformer, the voltage that appears across the secondary winding is equal to the voltage that's applied to the primary windings times the turns ratio. So let me give you an example here. So in a 4-to-1 step-up transformer, so for every 100 turns on the primary side, there's 400 turns on the secondary side. That makes it a 1-to-4 step-up transformer. If you put 10 volts AC on the primary side, that will yield 40 volts across the secondary side. That's that 1-to-4. So it's a step-up transformer with a factor of 4. So 10 volts would yield 40 volts on the secondary. One thing to keep in mind, transformers do not create power. The power has to be equal on both sides. So you may be stepping up the voltage on the secondary side, but the current through there will be less. When you build a step-up transformer, especially if it's a power transformer, you're probably going to have higher current in the primary. So quite often you'll see larger gauge wire used for the primary of a step-up transformer. Transformers don't know which way is which. They don't know which is primary and which is secondary. They'll function even if you're hooked up backwards. There's a question in the exam if you have, I think it's a 4-to-1 step down transformer and you hook it up backwards, what's going to happen? Well, it's going to act like a 1-to-4. Okay, and then here's one of the questions that describes this whole concept or demonstrates this concept. The question is, if you have a transformer with 500 turns on the primary and 1500 turns on the secondary, and you apply 120 volts on the primary, what are you going to get out of the secondary? Well, 1500 divided by 500 is 3. So it's a 1 to 3 step-up transformer, 3 times 120 volts on the primary, 360 volts on the secondary. Okay, things get a little fuzzier when you get into impedance transformation. It does follow the turns ratio, but in order to calculate that turns ratio, you have to know the primary impedance. You have to take the primary impedance and divide it by the secondary impedance, and then take the square root of that. And the one question on in the pool is if you're trying to match a 600 ohm feed point to a 50 ohm coax, what turns ratio do you need on that impedance transformer? Well, 600 divided by 50 is 12. Square root of 12 is 3.5. Answer 3.5 to 1. One other question you'll see perhaps on the test about impedance transformation. Yeah, you can use a transformer to do it, but RF impedance matches. In addition to using a transformer, there's a circuit called a pi network. You can also use a length of transmission line to create an RF impedance match. All right, time for the fast money round here, folks. What is impedance? Well, remember, impedance is very similar to resistance in that it's the ratio of voltage to current in an AC circuit. What's impedance? Ratio of voltage to current. What occurs in an LC circuit at resonance? What happens at that magic point? Well, the current voltage are equal, resistance, none of that makes any sense. Inductive reactance and capacitive reactance cancel each other. They're equal and they cancel out when an LC circuit is resonant. Okay, how does a capacitor react to alternating current? As a frequency is applied, reactance decreases, reactance increases with increasing frequency. You can eliminate the two bottom of these. Amplitude has nothing to do with it. It's purely frequency. So if you're not sure, like Mike said, a lot of times you can toss out the two ridiculous ones and leave yourself a 50-50 chance. But as the frequency of the applied AC goes up, the higher the frequency, the lower the reactance in a capacitor. And that's what resonance is. Resonance is the sweet spot where at that frequency, the reactive capacitive reactance is going down if you're going up in frequency, and the inductive reaction is going up. At a point where they equal and cancel is resonance. Okay, hey, I think we just saw this one. What's the voltage output of a transformer? 500 turn primary, 1500 turn secondary, when 120 volts is applied. Okay, 500 divided by 1500 divided by 500, that's a 3. So 3 times 120 volts AC, you're going to have a 360 volts on the secondary. Okay, what letter is used to represent reactance? The letter X. Okay, I'm going to pop this up here just for a quick refresher, because we kind of went through some of this already with the milliamps instead of amp. You'll need to know these. You'll need to even know, this is showing pico, micro, milli. You'll actually need to know nano as well, only for one question. But refresh yourself with these. Let's talk about series circuits. What are series circuits? It's where the components are connected end to end. And if it's a DC circuit, the same DC current flows through all of the components. What goes in one end comes out the other. If you have a parallel circuit, which I guess I left my title off there, in parallel circuits, components are connected side by side, as the name implies, parallel to each other. The same voltage appears across all of the components in a parallel circuit. So let's talk about resistors in parallel. Boy, so the most important concept is the total current is equal to the sum of the current through each resistor. So if you have three resistors sitting right next to each other in parallel, the total current going through the circuit is going to be equal to the sum of the current through each resistor. I picked these numbers. Let's see. And just as an example, we'll apply Ohm's law. We have a 10 ohm, a 20 ohm, and a 50 ohm resistor. We've got 10 volts applied across it. Well, that 10 ohm resistor is going to allow 1 amp to flow. I'm sorry. 20 ohm resistor is going to allow half an amp to flow. And the 50 ohm resistor is going to allow 2/10 of an amp to flow. That's a total of 1.7 amps. So what's the effective resistance of those three resistors in parallel? Well, we'll use Ohm's law. R equals E divided by I. E is 10 volts. We have 1.7 amps. So those three resistors in parallel is equivalent to 5.9 ohms. That's interesting. Notice that the effective resistance is lower than any of the individual resistors. That can help you find the right answer. Okay, so you can go through Ohm's law like I did there, or you can use some formulas to calculate resistance of two resistors in parallel. The equivalent resistance is the product of the two resistances in ohms divided by the sum. Okay, 100 and 200 in parallel. That's 100 times 200 divided by 100 plus 200, 20,000 divided by 300. Answer 66.6 ohms right out of the test. Again, notice the effective is lower than either of the two resistors. What happens when you have three resistors in parallel? Well, the equation is um, you take the inverse of each resistance and add them together, and then take the inverse of that. So, hey, you got a 10, 20, and 50 ohm resistor in parallel. I've heard this somewhere before. Let's do the math this way. You'd have 1 over 10, 1 over 20, 1 over 50, 0.1, 0.05, 0.02. You add those up, that's 0.17. You take the inverse of that, 15.9 ohms. Hey, that's the same answer we got here, the same values. So that's how you do resistors in parallel. Oh, thank God. Resistors in series, much simpler, because when you have resistors in series, the resistance is additive. All you have to do is know how to add the numbers. So if you had a 10, 20, and 50 ohm resistor in series, you add them up and come up with an effective resistance of 80 ohms. Oh, let's talk about inductors. They're basically the same. They behave the same as resistors. If you have two inductors in series, you simply add the two values. So if you have a 20 millihenry and a 50 millihenry inductor in series, they're going to give you the equivalent of 70 millihenries. Parallel, you do the same kind of calculation that you would with a resistor. So 3 inductors in parallel, let's plug in the numbers. If they're all 10 millihenry inductors, you'll come up with 1 over 0.3 and the answer of 3.3 millihenries. Capacitors, they got to be different. They behave just the opposite of resistors and inductors in that they are additive when they're connected in parallel. So if you have 3 capacitors in parallel, you simply add up the values. Now, this is the one where you have to know nano and pico. You're given the value of 2 of the capacitors as nanofarad, and you're given one as 750 picofarad. Well, it's a factor of 1,000 different. So yeah, take 750 divide by 1,000 to convert to nanofarads. And if you add those up, the correct answer for that question is 700 or 10.750 nanofarads. Just as you flip flop the with resistors, when connected in series, instead of being additive, they're actually the values reduced. So if you have 2 capacitors in series, we'll use the same formula here. You have a 20 and a 50, so it's the product divided by the sum. That works out to a 20 and a 50 in series is going to be the equivalent of 14.8 microfarads. 3 capacitors in series. Oh, look at that. 1 over 100, 1 over 100. Okay. Yeah, that math works. 3 100 microfarad capacitors in series are going to be the equivalent of 33.3 microfarads. Okay. Mind numbing, I know. We're just about done. I want to give you some shortcuts here to remember. You might have noticed, you might not have, but when resistors and inductors are in parallel, or capacitors which are in series, those are those formulas where you got to invert this and take the inverse of that. If all components are equal value, it's a very easy calculation. You just divide the value of one of the components by the total number of components. So if you have 4 100 ohm resistors in parallel, 100 divided by 4, they're equivalent to 25 ohm. That's quicker than going through the calculations. Likewise, if you have 3 100 microfarad capacitors in series, which we just saw, you take 100 and you divide it by 3 and you come up with the same answer, 33.3 microfarads. There's a shortcut. Another thing to keep in mind, and one of the questions is, if you need to increase the inductance in a circuit, how do you do it? Well, since inductance is additive in series, you would add an additional inductor in series to increase that inductance. Converse with capacitance. To increase the capacitance in a circuit, you'd need to add a capacitor in parallel. Okay, a few more questions and we're out of here. And a little more than 40 minutes. Sorry about that, Mike. So what is the inductance of 3 10 millihenry inductors connected in parallel? Well, I just said if they're all the same value, you can take that the value of one of them and divide by the total number of them. So 10 millihenries divided by 3, that's a quick shortcut to 3.3 millihenries. Also notice you can eliminate the first 2 ones because we're not changing scale. Everything's in millihenries. So 0.3 henries or 3.3 henries, don't even give them a look. Just remember, you can divide that by 3 because they're 3 equal valued components. Okay, what's the total resistance of a 10, 20, and 50 ohm resistor connected in parallel? Well, we did the math on that one in a couple of ways. So we used Ohm's law, we used the formula. Answer doesn't change. It's still 5.9 ohms. Again, there's only 2 possible ones here because 17 is more than 10, 80 is more. The fact that the composite is going to be less than any of the individual ones eliminates those 2 from contention. Okay, why is the primary winding wire of a voltage step-up transformer usually larger size, larger gauge than that of a secondary winding? Well, that's because transformers do not create power, so you are actually going to have to be able to accommodate a higher current in the primary. You want a larger gauge wire to handle that higher current with less voltage drop. I think we're just about to the end here. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary? What's the mechanism that makes a transformer work? Mutual inductance. That's it, folks. I hope you survived. That's the end of the G3 electrical principles. And I'm Tim Hanna, WB9NJS.
Okay, so this circuit diagram, I have no idea what it does, but this circuit diagram will appear on the test, and they will ask you to identify the components, and you'll notice a lot of the components have numbers. And so there are what, 5 questions in the pool. You'll probably have 1 or 2 of them, and they'll ask you to identify those questions. Now, I would recommend that you go to page 4.9, figure 4.4, which has all of the major normal schematic diagram symbols, because you'll just need those. No matter what, you'll need those. And so we're going to go through the 5 questions on the pool, but it's a good idea to know that stuff anyway. So the first question is, where is the field effect transistor? Which device is the field effect transistor? And It's this one right here. That's not the most common, but that's one of the symbols for a field effect transistor. The next one is Zener diode. What's the symbol for a Zener diode? Zener diode is a voltage regulating diode. It has a characteristic voltage, and this is the Zener diode. It's a diode symbol, but it's got these two little wiggly extra arms on it. And that's a Zener diode. That's a regulator diode. So the voltage at this point, with relation to ground, will be fixed. If it's biased correctly, will be fixed and will help regulate the voltage on that line. The next one is an NPN junction transistor, and there's only one junction transistor on here. That's this one. And if the arrow points diagonally toward the bottom, that's an NPN. If the arrow points the other way, it's a PNP. That has to do with the way it's biased. You don't need to know that for the test, but this is an NPN. The answer is 2. This is an NPN junction transistor. Now, remember we had a field effect transistor, that's this. This is a junction transistor, or a BJT. The next is a solid core transformer, and Tim was talking about transformers. Well, there's only one transformer on here. That's this one, number 6, is a solid core transformer, and the schematic of it has the 2 windings. Tim was talking about the turns ratio. It has the 2 sets of windings and these 2 little bars that indicate that there's a core. You can also have a transformer without a core, but this is a solid core transformer. And the last test is a tapped inductor. An inductor is a coil, but not a transformer. And so this is a tapped inductor. Inductor is a coil, and the tap is this one here. So it's a 3-lead device. It's a tapped inductor. And again, I would really recommend you study the schematic symbols, because these will come up over and over again. Okay, so I'm going to go through some practical circuits, and I'll try to use actual schematic diagrams to be able to, as examples. So what is the function of a bleeder resistor in a power supply? Well, if you notice, the very last phase part of this power supply, if you can see it, is a capacitor. And if you ever have a piece of electronics and you turn it off and the pilot light stays on, well, that's because this capacitor hasn't discharged yet. So there's a resistor past the capacitor that is to bleed off that extra voltage on the capacitor. So B, it discharges the filter capacitors when the power is removed. And by the way, in the kind of power supply that you will have with your ham radio, that's going to be 12 volts. But I actually worked on a high voltage pulse modulator where the voltage on the capacitor was 50,000 volts. So you really need to be aware of the voltage on capacitors even when the power is removed. Which of the following components are used in a power supply filter network? Diodes, transformers and transducers, capacitors and inductors. All these choices are correct. Well, you don't have transducers in a filter network, and you probably don't have diodes in a filter network. So the answer is capacitors and inductors. And this is an example of a filter network that might be on the output of a power supply. There's an inductor in series, a capacitor in parallel, and then a bleeder resistor or a load resistor out here. And by the way, Tim talked about inductors and capacitors. And one way to remember the reactance is that an inductor is just a wire at DC, and its reactance goes up as the frequency goes up. A capacitor is just 2 parallel plates. And so for DC, it's an open circuit. But as the frequency goes up, the reactance goes down. So if you ever get confused, it's easy to remember what the capacitors and the inductors do. Which type of rectifier circuit uses 2 diodes and a center tapped transformer? A full wave bridge, half wave, or synchronous? Well, I don't know what synchronous means. The answer is a full wave, but not a full wave bridge. We'll talk about a full wave bridge in a minute, but with a center tap transformer, as long as the transformer is twice the voltage that you're trying to get out, you can get by with just 2 diodes, and this is the pulsing AC or pulsing DC that you get out. That would then go into a filter, but the answer is full wave, not a full wave bridge. And I'll show you an example of a bridge in just a second. But the advantage of this kind of circuit is that you only need 2 diodes. The disadvantage is that you need a transformer with an output twice the voltage of what you want out. What is the characteristic of a half wave rectifier in a power supply? Only 1 diode is required. The ripple frequency is twice that of a full wave rectifier. The more current can be drawn. The answer is only one diode is required. This is the simplest possible transformer. I mean, simplest possible power supply. You have an AC voltage. You rectify it with one diode. There's a load resistor, maybe some filter capacitors, but the diode only conducts half the time. So it's 180 degrees of the 360 degrees, and it's back biased the other half. So this is by far the simplest and cheapest type of power supply. It's the worst for quality, but if you just need something quick and dirty, this is what you use, one diode. What portion of an AC cycle is converted to DC by a half wave rectifier? We just looked at a half wave rectifier, and so if the whole cycle is 360 degrees and it's only doing half, that's 180 degrees. So B is the answer. Next is, what portion of an AC cycle is converted to DC by a full wave rectifier? And I just told you the answer to that. If a half wave is only 180 degrees, twice that is 360. This is the full wave rectifier. Two diodes. When this goes positive, this diode conducts. When this goes negative, this diode conducts. And so you've always got a positive pulsing DC output. So the answer is 360 degrees. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? A series of DC pulses. DC means it's only flowing in one direction, twice the frequency of the AC. A series of DC pulses the same frequency as the AC. A sine wave at half the frequency of the AC. I don't know how that would happen. Or a steady DC voltage. Well, it can't be half. And if it's unfiltered, it can't be steady DC. So it has to be one of these two. And so the answer is DC pulses twice the frequency. So the frequency, this is one cycle. The frequency is two peaks. And so the DC pulses at twice the frequency of the AC input. And if you ever get confused and you just draw this circuit, you can say, okay, when this goes positive, the current flows this way, and it doesn't flow this way. This is back biased. When it goes negative, you get positive here, and this is back biased. And so you can just figure out how the current flows just thinking about it. Which following characteristic of a switch mode power supply compared to a linear power supply? This is probably an important thing to know as a ham radio operator, because you're going to be faced with buying a power supply for your base station. So faster switching time makes higher output voltage possible. Fewer circuit components are required. High frequency operation allows the use of smaller components, inherently more stable. Well, it's got to be this, and you'll find that when you go to buy a power supply, the switching power supplies will be much cheaper than the linear power supplies. And if you get a good one, it should be fine. But in general, switching power supplies have more noise. And so if you bought a cheap power supply and you're having noise problems with your radio, it could be that you're using a switching power supply. The advantage of a switching power supply is that because you're not dealing with the lower voltage AC, you can use smaller components, and therefore it's much cheaper. What's the purpose of a neutralizing amplifier? We're going to get into some stuff here where if you really want to get into it, you're going to have to read the book. Just for the purpose of this review, just remember that a neutralizing amplifier is to eliminate oscillations, eliminate self-oscillations. We're not talking about modulation. We're not talking about cutoff, and we're not talking about carrier frequency. So the eliminate self-oscillations is the answer. Classes of amplifier, we should probably have a separate slide on this, but classes of amplifier are something that's just in general very well known and a good thing to know. And so I'll just review. Class A is the most accurate. Class C is the most efficient. So which of these classes has the highest efficiency? It's Class C. The problem with Class C is it also has the most distortion. You get the best power out of it, but the output waveform rarely looks anything like the input waveform. So a Class C amplifier is used when you just need raw power and not necessarily fidelity. Which of the following, okay, now we're getting into digital. Which of the following describes the function of a two-input AND gate? This is probably the simplest digital question you'll ever have. Output is high when either are low. Output is high when both inputs are high. Output is low when either input is high, or output is low when both inputs are high. The answer to this, if you're looking at digital outputs, you always want to look at the truth table. And by the way, you can always look this up, or you can just create one. But the function is and, which means that you have to have a 1 on A and a 1 on B to get a 1 on the output. That's how it works. Anything else gives you a 0. And so this is far and away the simplest digital question you'll ever have. But if you always go back to the truth table, you shouldn't have a problem. A Class A amplifier, I already told you about this. A Class A amplifier, what percentage of the time does the amplifying device conduct? 100%, more than 50%, 50%, less than 50%. Well, Class A is the most accurate, but the least efficient. So you're going to be conducting 100% of the time, though not necessarily with as much efficiency as you might have with a Class C, for example. Another digital question, how many states does a 3-bit binary counter have? Well, anything that's digital, the number of bits is the exponent of the power of 2. And so the principle is the number of states is 2 to the n, where n is the number of inputs. So if you have 3 inputs or 3 bits, this is 2 to the third, which is 8. Okay, if it was 2 inputs, it would be 4. If it was 4 inputs, it would be 16. So 2 to the n, or 2 to the number of bits, is 8, and the answer is 8. What is a shift register? A shift register is a clocked array of circuits that passes data from in steps along an array of operational amplifiers, a digital mixer, or an analog mixer. Well, right away, we're talking about a digital circuit. So it's not going to be op amps and it's not going to be an analog mixer. Might be a digital mixer, but it's really a clocked array of circuits that pass data steps along the way. Very common type of digital circuit. Which of the following basic components of a sine wave oscillator? In all of your radios, you'll see a lot of oscillators used for lots of different purposes. And oscillators are one of the basic circuits you really need to understand. So the choices are an amplifier, a divider, a frequency multiplier and mixer, a circulator and filter operating in a forward feedback loop, or a filter and an amplifier operating in a feedback loop. Well, we didn't talk about mixers and we're not talking about circulators. So it turns out that if you have an amplifier and a filter, you can make that into an oscillator. You just need positive feedback. So the answer is D. This is an example of an oscillator, and the frequency is determined by, Tim talked about resonance. It's the resonance of these capacitors and this inductor, and the transistor here creates the gain, and it'll just run at a certain frequency based on what we calculate for these components. The block diagram is you have amplifier and you have positive feedback at a certain frequency, and that's what gives you the voltage out as an oscillation. Very common circuits in ham radio. How is the efficiency of an RF power amplifier determined? We're talking about efficiency and an RF power amplifier. So RF is the output. The efficiency is how much power it uses. So DC input power divided by the DC output power. We're not looking at DC output power. RF output power divided by the DC input power. That sounds right. Multiply the RF power by the RF input power. Well, there really isn't any RF input power unless you're looking at the receiver, or add the RF power to the DC output. That doesn't make any sense. So the answer is divide the RF output power by the DC input power. That gives you the efficiency of the RF power amplifier. What determines the frequency of an LC oscillator? Tim actually talked about this a bit. The answer is, it's not the number of stages and it's not the time delay, it's the capacitance and inductance. And again, we'll look at that other oscillator. The capacitance and the inductance determine the frequency. And you set these up at resonance, and that'll determine the frequency of the oscillator. Again, back to amplifiers. What of the following describes a linear amplifier? Any RF power amplifier used in conjunction with an amateur transceiver? That doesn't make sense. An amplifier in which the output preserves the input waveform, a Class C high efficiency amplifier, or an amplifier used as a frequency multiplier. Well, we're looking for linear, so Class C is not linear, so it's got to be B, an amplifier where the output preserves the input waveform. Which of the following modes is a Class C power stage appropriate to amplifying modulated? It turns out that Class C is the least fidelity, and with both SSB and AM, you really want the amplitude to be as accurate as you can. So the answer here is FM, because the modulation happens at frequency, not amplitude. So class C works fine for FM. What circuit is used to select one of the sidebands from a balanced modulator? Carrier oscillator, the filter, IF amplifier, RF amplifier. It's the filter. And when you're talking about selecting in sidebands, you're really always talking about a filter. What is the output produced by a balanced modulator? So a balanced modulator. So we should talk about sidebands. So the way sidebands work, I mean, we say single sideband and throw that around a lot, but you really need to understand that the way a sideband is generated is that if you have a carrier and then you modulate it, you get two sidebands, and the sidebands are the sum of the frequency and the difference of the frequency, and that's used in all analog radios to both detect and to transmit. So this is not single sideband; this is double sideband modulated RF. It's got the lower sideband and the upper sideband. And just by the way, and this isn't on the test, but by the way, the reason you use sidebands is that most of the energy goes into the carrier, a lot less energy goes into the sideband. And the sideband has all the same information if you can detect it right. So the reason we do SSB instead of AM is that it's much more efficient. What's one reason to use an impedance matching transformer on the transmitter output? To minimize transmitter power output, I don't know why you'd want to do that, to present the desired impedance to the transmitter feed line, to reduce power supply ripple. We're not talking about power supply, and we're not talking about radiation resistance. So the answer is B, to present the desired impedance to the transmitter feed line. This is called matching. And this is one of the most important things you'll learn how to do with your radio. How is a product detector used? So a product detector is used on a single sideband receiver to extract the modulated signal. And if you want more information about this, look in the book, because we'll go down a rabbit hole if we try to explain this in detail. Which of the following characteristics of a direct digital synthesizer? Extremely narrow turning range, relatively high power output, pure sine wave output, or variable output frequency with the stability of a crystal oscillator? Well, this is why we're getting into more digital in the radios, and that is that in the very old days, when I first got interested in ham radio, if you wanted a stable oscillator, you used a crystal, and if you wanted to change frequencies, you had to change crystals. The crystals are very stable, but it's not very convenient. You can't just tune. So the advantage of direct digital synthesizers is that you can vary the output frequency and still get the same stability as you would with a crystal oscillator. Which of the following is an advantage of digital signal processing compared to analog? So again, getting back to the crystal issue or the analog issue, is that you can get much more frequencies and a wider range of filters using digital than you can with the analog techniques. And again, this gets into a lot of detail that if you want to pass the test, just memorize this answer. If you want more detail, look in the book. What term specifies the filter's attenuation inside its passband? Now here we're going to talk about 3 dB again, but the answer is insertion loss. We'll get to 3 dB in a minute. What parameter affects the receiver sensitivity? Input amplifier gain, the demodulator stage bandwidth, the input amplifier noise figure. Those all seem right. I think the answer is D. All of these are correct. What is the phase difference? Okay, we're getting at SDR, software-defined radio. We could spend a whole 2 hours just talking about software-defined radio, so I'm just going to give you answers, and if you want to understand these better, go to the book. What's the difference between I and Q? Q is the quadrature signal, and it's used to detect RF signals for modulation and demodulation. Quadrature is 90 degrees. That's why it's quadrature, 1/4 of a cycle, 90 degrees. And so the key for I and Q in RF signals is 90 degrees. That's why it's called Q or quadrature. And again, if you want to get into SDR, read the book. What's the advantage of IQ modulation with software-defined radios, SDRs? All types of modulation can be created with appropriate processing. The software-defined radios work by taking the RF signal and immediately converting it to digital, and then doing all the processing in digital, and then just before it comes out as at the end, you turn it back into analog. So it gives you much more capability at various frequencies than you would have with traditional analog circuits. Again, software-defined radio. Which of these functions are performed by the software in software-defined radio? Filtering, detection, modulation, all of these choices are correct. What is the frequency above a low-pass filter's output power less than half of the input power? This is where we talk about 3 dB. So it's called the cutoff frequency. This is a frequency response curve. This is done logarithmically. So this is not, this is 10 times this is 10 times this, but the cutoff frequency is the 3 dB point. In other words, the half power point that Tim talked about, the 3 dB point, is the cutoff frequency. A notch frequency would be for a notch filter. I don't know about roll-off frequency and Nieper frequency. I don't know what those are. So the cutoff frequency is the 3 dB point on a low-pass filter. What term specifies the filter's maximum ability to reject signals outside its pass band? Well, again, if we look at the bandwidth, the 3 dB point determines the bandwidth, and the ability to reject signals is any frequency out here or any frequency out here. In other words, the signals lower than 3 dB will be rejected, and that's called the ultimate rejection. Again, it's not notch, it's not roll-off, it's not insertion loss, it's ultimate rejection. Bandwidth of a bandpass filter is measured between what two frequencies? The upper and lower half power, the cutoff and roll-off, the pole and zero, and the image and harmonic. I think we just looked at that. It's the upper and lower half power. So the half power, Tim talked about this, half power point is the 3 dB point, and the bandwidth is the distance, the frequency between these two half power points. In ham radio, you'll hear the 3 dB point a lot.
And those will be posted on the McCark site. That's how you'll be able to watch these videos after the class. Eventually, they'll be posted on the McCark site. You'll be able to access them and watch them. And
all of the, as far as I know, all of the instructors are willing to answer questions. So email is probably best, but maybe Steve can distribute email links for us to the participants. But if anybody has questions, we're happy to help.
And that book is really quite a resource. It's a little pricey, 30 some bucks, but you'll find that it's good as a reference, just in explaining some of the things. And again, there's the material is very broad in what it covers. There may only be 3 questions that come from the pool of 40, but it's covering all kinds of different topics and concepts. So if you want to avoid just memorizing the answers, and there's nothing wrong with that, but if you want to avoid that and maybe have it make a little more sense, get the book, read the pages, look for the explanations. And if you get into that into a portion of the book and you're just scratching your head and it's only confusing you, jot down the question and either email it to us or next week come back with a question and we'll try to clarify.
Yeah, and even though I'm not presenting next week, I'll be available in the class too. So I think Tim too.
And I would like to add just one thing. I start the Zoom meeting a half an hour before the class starts. The reason I do that is so that people can sign in and make sure they have the Zoom working. I've had a lot of people who try to sign in right as the class is starting and they have Zoom problems and then they miss part of the class. So if anybody is not really familiar with Zoom, I'm here early and you're welcome to come in early and we'll chat.
Yeah, that's a good point, Mike. If you get here early next week, it's a good chance to pass along questions. And this was kind of a rough night because we covered so much material. So if you're feeling slightly overwhelmed, don't worry about it. I would expect that given the the depth and breadth of topics covered tonight. Should be a little bit easier in the coming weeks. We won't be trying to tackle quite so much information.
And I would just recommend, I mean, the way I studied for these tests is using the hamstudy.org website. And it's just, if you just give yourself test after test after test, you'll figure out what you know and what you don't know. And what you don't know, you either look in the book or ask us, because that's how you learn. And you'll find that if you just do a bunch of practice tests, you'll figure out what you don't know and what you need help with. It works.
Just another note. In addition to the videos, in the past, we've made available PowerPoint presentations themselves. I will be making mine available along with what I call a study guide. Basically, it's the script that I developed the PowerPoint from. But those documents, we'll try to make those available too. So give you something else to look at and maybe some additional direction.